This is a state space modeling exercise for chemical process control. We're going to go through this activity that's shown here, and in order to be able to access this activity and the files for it, you'll need to go and visit the internet. Go to APMonitor.com and visit the process control course, and then if you scroll down and visit class number 32 is where we talk about state space modeling, and you can access the files and the document here. Okay, so I'm going to go back. I'm just going to work with that from this document. Okay, so we have a reactor, and here we have reaction A going to B, and then we have two things coming out. We have A and B coming out. We're interested in the concentrations of those coming out of the reactor. We have an exothermic reaction taking place. It's well mixed, but there's also a jacket here. And so we have a cooling temperature, Tc, and then we have two inputs. We have an inlet temperature. Okay, so this is the inlet, and we have an inlet temperature and inlet concentration of A, and we're trying to convert this to B. Okay, and we have this data up here for the nominal cooling jacket temperature, the flow rate in meters cubed per second, the volume in meters cubed, the density. Okay, so we're assuming that A and B have equal densities and also equal heat capacities. We also have a heat of reaction as well. We have an E over R value, that's our activation energy, pre-exponential factor K naught. Okay, so that K naught comes in right here in the pre-exponential factor. And then we also have an overall heat transfer coefficient. Okay, so the heat that's transferred between the jacket and the reactor, that's going to be a UA Tc minus T. Okay, for the heat that's transferred from one to the other. And then we also have a nominal feed concentration, a feed temperature, concentration in our reactor, and then a temperature just as our starting point. Okay, so what we want to do first of all for deriving this state space model is go ahead and write an equation for each of our outputs that we're interested in. In this case, we want to try to get concentration of A and then also temperature. Okay, so we want to be able to write equations that describe both of those, and so what we're going to need for this one for CA is a species balance. And then for temperature, we're going to need an energy balance. Okay, and just a couple other things to note is a first order rate constant, first order reaction rate. We have our rate constant K, which is a function of temperature, a typical Arrhenius expression for that reaction. Okay, so what I'm going to do now is go ahead and just write a species balance for A. This is just a mole balance. Actually, I shouldn't put the dot there at the top of this one. And minus. Okay, so I have the accumulation equals in minus out, and that relates to concentration. If we assume that the volume is constant, and it's well mixed, I'm going to just assume that concentration A accumulating in the reactor is equal to what's coming out. Okay, and then we have Q, that's the volumetric flow rate. Okay, and then that's times CA in, coming into the reactor, minus Q times CA going out of the reactor. And then we also have a reaction term as well. So what's leaving is also K naught exp e to the negative E over RT. Okay, then times my concentration of A times a volume. Okay, so this equation right here represents this is the species balance, and it will allow us to be able to calculate the concentration coming out of the reactor. But we also know that the temperature, this temperature is going to be changing, and that's going to affect it as well. So we actually need to solve two equations together. We'll need to solve an energy balance. Okay, so this is our energy balance now, and very similar to the species balance, but instead of Na, it's going to be the enthalpy an enthalpy balance that we're going to use for this. Okay, so you have in, out, and then plus the reaction. Okay, the reaction rate. And I guess I should have written that up here, reaction rate as well on the A. Species balance. Okay, so now let's go ahead and relate the enthalpy to temperature. Okay, so that's going to be m c sub p dt. Now mass is also, based on the variables that I gave you at the start, that's going to be rho times the volume. Okay, so rho times the volume equals the mass. And then I'm just going to go ahead and start writing this in terms of temperature. I have rho c sub p times the volumetric flow. Okay, and then I have my temperature coming in into the reactor minus the temperature leaving the reactor. So that's just a combination of these two. Okay, actually there's one other one. This is going to be the delta H of the I'll put heat transfer here. Okay, the heat transfer between the jacket and the reactor. Okay, so let's go ahead and do the reaction as well now. So that's going to be plus delta H of my reaction times the rate of the reaction times the volume. Okay, and then I also have my UA, and then it's going to be temperature cooling jacket minus temperature. Now I always forget which one is going to be the negative or positive sign. So in this case, if the temperature of the cooling jacket is higher than the temperature of the reactor, then we know the temperature is going to increase. So with all else being the same, if this is a positive number, it's going to make my derivative value here positive as well, meaning that the temperature is going to be going up. Okay, so that's one way to remember the sign on this one, that with a positive value here, Tc greater than the temperature, then my temperature of my reactor with respect to time is going to be increasing. Okay, so so I think we have the right signs on everything. Now I'm going to also expand this just a little bit more. My reaction rate, if you remember, you got to combine this into the substitute this K into this expression. That becomes your rate. Okay, so that's going to be a function of temperature. Okay, so let's go ahead and substitute everything else in here. So it is a function of temperature, and then it will be rho v c sub p dt equals rho q c sub p ti minus t plus delta h reaction rate. Okay, now I'm going to go ahead and substitute in my k naught exp e to the negative e over rt. Okay, and then put my Ca, and then I also need my volume there, and plus UA Tc minus T. Okay, so I've got my two expressions, this one for temperature. Okay, this is for temperature, and then this one is for my concentration of A leaving the reactor. Okay, so I have my two balances. Let me just show you really very quickly. This is included in the files, although it's really not the subject of the tutorial here. But if you open up these files and just go ahead and unzip, you'll see a CSTR nonlinear and then a linear. If you open up the nonlinear, we'll just go into how we can solve this with MATLAB. Okay, so if you open up CSTR1, that's the function here. Okay, so we have all of our values that I gave you before. Okay, those are just all the parameters from the model. We also have our states. These are inputs. Okay, so they're coming in right here along with time. And then what we need to return is a function that returns the derivative values as you change the states x. Okay, and so here are our two equations that we just wrote, and those two equations, those will return the derivative values. X dot 1, that's going to be for concentration of A, and then x dot 2, that's for temperature. Okay, and then once you have this function, then you can have an ODE solver solve it in MATLAB. Okay, and so I have a step response just as an example, just setting up some steady state initial conditions, my cooling jacket temperature. Okay, and then here's where I solve it with an ODE solver, and the rest of this is just plotting it. Okay, so if I run this, I get a step response here for my jacket temperature, which is 300, and then I get a steady state condition for my CA, and then also my temperature. Okay, so I simulated the nonlinear system. But let's suppose that we want to get this linearized. We want to be able to get this into a transfer function form or into a state space form. And so let's go ahead and continue on with the exercise here, getting these species and energy balances into a transfer function form. Okay, so what I'm going to do is just come down here a little ways, and let's go ahead and linearize these expressions. Okay, so what I'm going to do is go ahead and just transfer my species balance. Okay, so I have dCA dt. I'm just going to divide over my volume first of all, just to get that into a more standard form. Okay, so that's going to equal Q over V times CA in, and then that's going to be minus Q over V times CA out. Okay, and that's going to be minus K naught exp negative E over RT, okay, times CAV. Okay, and then my volume is going to cancel here when I divide over. Okay, so I've got this into a standard form. Let me go ahead and linearize it. Okay, so when I'm linearizing any function, okay, so let's say it's of x and y, it's just the nominal values. Okay, the steady, in this case these are going to be steady state values, and then plus df dx at the nominal conditions, x minus x naught, plus df dy at the nominal conditions, y minus y nominal. Okay, so we have this for our linearization equation, and when if we say that it's going to be going to steady state, then this is going to be 0 because the time derivative of this function is going to be 0 because I'm at steady state. Okay, so I just need to take the derivative with respect to each of the variables, multiply it by this, which is called a deviation variable. Okay, and okay, so I'm going to go ahead and erase that, and let's go ahead and get a linearized expression here. Okay, so that's going to equal Q over V CA in minus CA in nominal condition. Okay, and then I'm going to also add, it's going to be negative Q over V. I'm going to take the derivative with respect to CA out, which is also equal to CA. Okay, and then it's going to be equal to negative K naught E to the negative E over RT. I've got to plug in the nominal condition here for temperature. Okay, that's no longer a variable, it's just a constant in the expression, and that's going to be CA minus CA nominal condition. Okay, that's going to become a deviation variable. And then let me go ahead and do the third one as well. Let me go ahead and take the derivative with respect to temperature. I'm going to call this, I'm going to call that K right there, the K value. And then when I take the derivative of this expression with respect to temperature, okay, then that's going to equal okay, that's going to equal negative K, and then I have this term right here, and that's going to be E over RT squared. And I plug in the nominal condition, and then I have temperature minus temperature nominal. Okay, so I have my first expression here, which is just my species balance, and what I want to do is get this into state space form. Okay, so state space form in this case is going to be dCA dt and dtemperature dt. Okay, the derivatives equal, and then this is just going to be a 2 by 2 matrix, 2 1 and A2 2, okay, times CA and temperature, plus, and then I have 3 inputs here as well, so it's B11, B12, B13, B21, B22, and B23. Okay, and that's going to be multiplied by all of my input disturbances. And if we go up to the top, let me go up here, we want to be able to get this with respect to those three inputs. Okay, so let's go ahead and write those in here in my state space form. Okay, so Ca in, temperature in, and then also the cooling jacket temperature. Okay, so I have my my system into this state space form, and I just need to, from my first principles model, I need to get A11 and A12. So let's go ahead and see what those are from my linearized model right here. So I have Ca in. Okay, so I have B11, and then this right here becomes B11. Okay, and then I also have times Ca. This is going to be this A11. Okay, so this expression right here then becomes A11, and this expression right here becomes A12. Now we have B11, A11, A12. What about B12 and B13? Well, those don't exist in the equation, so those are equal to 0. Okay, so those are just going to be 0 values. Okay, now we can do the same thing. We can do the same thing for the energy balance right here. We can go ahead and linearize that and then get the expressions. I'm just going to go ahead and write those out for A21. Okay, now this is for the temperature, okay, so that's just going to be the derivative with respect to concentration, and so that's going to be delta H R K naught E. Now this one's a little bit more complicated. It's an energy balance, a few more terms involved. Okay, then A22 is going to be, now this one's really involved here. This one's a lot of expressions, easy to get get something wrong here. So I always need to go back and check my work after I'm done. I'm just going to write K here, but that's a function of temperature. You just have to plug in the nominal values, and then it's going to be E over RT nominal value squared times V. Okay, and then I also have negative U over A. Actually, I forgot to divide through by the numerator part. Okay, and this also is divided by through. Sorry, not with the numerator, but the term on the left-hand side of the expression next to the derivative. Okay, and then I could also do the same thing for B21, B22, and B23 as well. Okay, so I have this in state space form. I'm just going to show it to you in the MATLAB script. Okay, so if I go back to this example right here, and I go over to the CSTR Linear, I'm just going to open this up, and again I have all of my values here, my steady state conditions, and I compute K and the rate as well, and I just plug in the A, B, C, and D. Okay, so I'm going to run this, and I'll change folders here, run this example, and it'll come up with some step response models here. Okay, so this is the result. In one is the concentration coming in. This is the inlet temperature. Okay, in two, and then in three is going to be the cooling jacket temperature. Out one is the concentration of A, and that's the temperature. But let's go back to MATLAB just briefly here, and we'll run through some of these to get a system response. I had my matrices A, I have a B, I have a C, and I have a D matrix. Okay, to get that into a state space model, I just use the SS command, A, B, C, and D. Okay, and that gives me a state space. And then if I'm going to go ahead and close my plot, okay, and I'll do a step on my sys, which I just defined. Okay, so there's my system. I'm going to hold on to that plot and then make a discrete model instead. Actually, I'll do a transfer function model instead. Okay, so let's do a transfer function model, and that's just the TF command. Okay, and the argument of that is just the system that I want to transfer over. So I have 6 transfer functions there from input to output. And if you also open up this Simulink file, you'll see equivalent models here. Okay, so you have the state space model, which is right here. Okay, that's the state space model. And then here are the equivalent 6 transfer functions that we can also express this model in that form. So if I simulate this, let it simulate and open up this scope. Okay, I'm going to make that just a little bit bigger here. I keep missing that. Okay, so let me go back to MATLAB and Simulink and open up my scope. Okay, so there's my response, and then if I go back to my Simulink model, I also want to compare it to my transfer function model. And you'll see that the two are actually equivalent between the state space and the transfer function forms. Okay, so let me go back to here. And you can also do these in discrete form as well. So if you have a system discrete, you could do your continuous to discrete of system, and you also have to put in a sampling time. So if I did 0.5, for example, okay, then I have my discrete system. If I step that as well, then I'll be able to see the step response of the discrete system. You can see that only occurs at 0.5 second sampling intervals. Okay, so let me go back to the exercise here. What we can give kind of an overview of what we just did. We took a CSTR model. We derived a species balance and also an energy balance. Okay, so the energy balance right here. And then we linearized those expressions and then put them into state space form. We really only went through this first equation. Okay, this was our species balance, and the second row would then be our energy balance, and then put those into state space form. Came back over here to Simulink and simulated those as a state space model, and also as a combination of 6 transfer functions, and saw that those two were equivalent in terms of their representations and how you represent these models. Okay, so I'll post this video and others here in lecture 32, and feel free to access those and ask any questions if you want to.